It's going to encode that initializer function, which we've set to nothing. Then it's going to deploy our transparent upgradable proxy, and then it's going to call retrieve on the transparent upgradable proxy instead of our box. So let's do this. And perfect, we did it, right? It's returning 0 here. That's awesome. What we could also do is we could also do proxybox.store 1, and then we'll call retrieve. We'll see what happens here. Whoops, it's yelling at me because I got to do from account. Now let's go ahead and run it. And perfect. See, so after we stored on the proxy box, on this proxy, we're able to retrieve the value there. So this is fantastic. All right, now that we've deployed it, let's learn how to upgrade it. I'm going to change this to deploy and upgrade .py. And we're just going to do everything in here. So now that everything's deployed, let's go ahead and now upgrade this. So now we can always point to this proxy box address, and it's going to be the most recent upgrade. It's always going to have the code that we want it to have. So let's go ahead and upgrade from box that doesn't have that increment to box v2 that does indeed have this increment function. So let's try this out. So first thing we need to do is we actually need to deploy that box v2. So we'll do box v2 equals box v2 dot deploy. We'll say from account, and we'll leave it like that. Of course, we're going to have to import box v2 from Brownie. And right now, actually, let's even do proxy box increment. Right? If we call proxy box that increment from account, this should error, right? It shouldn't be able to call this increment function because that doesn't exist. Oh, and then we also changed the name of the script. Sorry. This is actually going to be deploy and upgrade. And perfect. We see it actually errors out here. It says, hey, box object doesn't have this increment function. You're crazy. I don't know what you're talking about. Well, good. That's what we want to do. So let's delete that line. Box v2. And we'll even do a quick little upgrade here. Now, all we need to do is call an upgrade function. Now, basically all we have to do is call this upgrade to function, right? But depending on if we've added a proxy admin contract, if we're using an initializer function, there might be a couple of different ways to go about this. So I like to just wrap everything up into its own upgrade function. You'll see what I mean in just a second. So what I like to do, again, we're going to pop into our helpful scripts, and we're going to create a new one called upgrade. Now for parameters in here, of course, we're going to take some type of account so that we have something to account to deploy from. We're going to use the proxy, which is, again, going to be that proxy contract, which is going to be our proxy contract here. We're going to need a new implementation address. We're going to need the proxy admin contract, which could be none. For us, we're going to have one, but it could be none. And then we're going to have an initializer, which also could be none. And then we're going to have the args for the initializer, which also could be none. Again, this star is a special thing in Python, which says any number of arguments will just get stored into this list called args. And perfect. This is going to be our function that's just going to take care of everything for us. So first thing, let's check to see if there is a proxy admin contract. So we'll say if there is a proxy admin contract, then we want to check to see if there's an initializer. What we're going to do is we're first going to want to encode that function data, of course. So we'll say encoded function call equals encode function data with the initializer and those star args. This is going to be the encoded initializer function here. Then all we have to do, and actually let's start with a blank transaction equals none. We'll say transaction equals proxy admin contract, since we're using one of these proxy admin contracts, since we've detected one, dot upgrade and call, since we also have an initializer. We're going to pass the proxy.address, new implementation address, and the encoded function call. And then of course, from account. So this upgrade and call, if we look in that proxy admin, there's this upgrade and call function right in the proxy admin, and it just calls upgrade to and call of the proxy contract. So hopefully don't let this bog you down a little bit, that there's kind of a lot of mix and matching going on, but this is what's going on. Oops, sorry, this is encoded function call, not encoded function data. Great. Now, if they don't have an initializer, well, what do? Well, we don't need to encode any function call here. We can just say transaction equals that proxy admin contract dot upgrade. So it has an upgrade and call. It also just has a regular old upgrade. So we'll just call upgrade, and we'll give it the proxy.address, the new implementation address, and then from account. Now, if it doesn't have a proxy admin contract, this means that the admin is just going to be a regular old wallet. Well, what do we do then? Well, first, check to see if it has an initializer still. And if it does, we need again to encode that function call. We can just copy and paste that there. And then once that's encoded, we can just call directly off the proxy contract. We're going to call exactly what that proxy admin contract is calling, which is going to be proxy.upgrade to and call. We're going to give it the new implementation address, the encoded function call, and then from account. And let's wrap this all up in a big else. So if proxy admin contract, do this stuff, else do this stuff. If initializer, do that. Otherwise, we can just do transaction equals proxy dot upgrade to, and then we just add that new implementation address from account. And then we'll finally return transaction. Whew. So I know that there's a lot here, but we're really just making this upgrade function really general. We could always just know, okay, if we're going to use a proxy admin, let's just do it like this. Okay, no, we're not going to use a proxy admin. We're also not going to use an initializer. Great, it would just look like this. But this is essentially all that we have to do. Whew. So now that we have our upgrade function, we can go ahead and use it here. So we need to give it an account, a proxy, a new implementation address. So we'll say account. So we'll say upgrade transaction equals upgrade account. We need a proxy and a new implementation address. We're going to give it the proxy. And we're going to give it box v2.address for that new address. We do have a proxy admin contract. So we'll say proxy admin contract equals proxy admin. And we don't have an initializer. So we can leave that part blank. Of course, we need to import this upgrade function from our helpful scripts. And this is all that we need. So now we can do print proxy has been upgraded. And what we could do now is we can do proxy box equals contract dot from ABI. We'll call it box v2. We'll give it the proxy dot address, box v2.abi. And now we should be able to call proxy box dot increment from account. And then we can print proxy box dot retrieve. And this should now be 1. And what we'll actually see is that this will return 2. Why does it return 2? Well, in our original proxy box, we stored 1. So it started with 1. We then upgraded to this new contract. And then let's actually just do a .wait, of course. We upgraded to a new contract right here. However, the storage of that contract stayed in the proxy. So that 1 stayed in the proxy. So even though we upgraded the contract, there's still 1 stored at the location in storage. So then when we call increment now, and then we call retrieve, it's going to go from 1 to 2. So let's go ahead and run this. Brownie runs scripts, deploy an upgrade, enter. And boom, that is exactly what we see output here. This is an incredibly, incredibly powerful and advanced feature. And if you've gotten to this point, you are on the border of being one of the most powerful smart contract engineers on the planet. Huge congratulations for getting this far. But we're not quite done. We, of course, need to write some tests because that is what's going to make sure our project always stays in sync and always stays up to date. So let's write a couple of tests here. So let's create a new file. We'll call test box proxy.py. And for this, we're really just going to test to see that our contracts work. We're going to see that this box actually is going to work correctly. So let's create a new test. Def proxy delegates calls. So we're going to make sure that we actually can delegate calls to our contract. We're going to say account equals get account, which means we got to do from scripts.helpful scripts import get account. Then we're going to do box equals box.deploy. Of course, this is going to be from account. Since we're using box, we're going to do from Brownie import box. We're going to do this proxy admin. So we're going to say proxy admin equals proxy admin dot deploy, of course, from account. Let's import proxy admin from Brownie. All right, so now we'll do the box encoded initializer function, or whatever we called it before. This is going to be that encode function data, which my VS Code actually automatically imported. Thanks, VS Code. And again, we're leaving it blank because we're not actually going to have a store there. And then we're just going to go ahead and run that deployment. So we're going to say proxy equals transparent upgradable proxy. And we're going to grab this from Brownie.deploy. We'll say again the box.address, proxy admin.address, box encoded initializer function. We're going to say from account, and then we'll give this a gas limit of 123. Now we're going to put the ABI on top of this proxy. So we're going to say proxy box equals contract.fromABI. We're going to name it box. This is going to be with the proxy.address and the box.abi. Of course, we're going to need to import contract from Brownie. And okay, so now we can assert proxy box dot retrieve, if I spelled that right, is equal to 0. Then we're going to do proxy box dot store. We'll do 1, and this will be from account. And then we're going to assert again this proxy box dot retrieve should now equal 1. So we're using this proxy contract. We've slapped the ABI on top of it, and this should work. So we're just testing to see that our proxy is working correctly. So we can go ahead and test this then with Brownie test. And beautiful, it passed. Now let's go ahead and create a new script for testing the upgrades. Create a new file, call it test box v2 upgrades.py, and let's do it. Called def test proxy upgrades. So account is going to be equal to get account. Hopefully at this point you're getting pretty good at writing these tests. From scripts.helpful scripts import, and of course we want to add this init.py just in case you forgot. So now we're going to import get account. Perfect. So we have our account here. Now, as you can see, we're doing a lot of this box equals box.deploy, deploy the proxy admin. It would probably make sense in one of your scripts to just write a deploy 3, to write a function called like deploy all or something like that. So again, if you guys want to learn more, if you want to improve upon this, I would highly recommend you go back and you make some of those improvements to really modularize this up. But for the time being, let's just keep going. So box.deploy from account. And since we're doing this, we're going to do from Brownie import box. I'm going to say proxy admin equals proxy admin.deploy. This will also be from account, comma, proxy admin. We're going to get those initializer functions. So we'll say box encoded initializer function equals encode function data, which we're going to grab from our helpful scripts as well. And then we're going to do the proxy again. Proxy equals transparent upgradable proxy deploy. We got to import this from Brownie as well. Whoops, not twice though. Deploy. It's going to have the box.address, proxy admin.address, box encoded initializer function from account, guess limit 123 123. All right. So we have the proxy deployed. We've already tested that this proxy works in this test box proxy, so we're not going to go ahead and test that again. What we're going to do instead now is we're going to deploy box v2. And we're going to update the proxy and make sure that everything still works. So we're going to do box v2 equals box v2 dot deploy. It's going to be from account, of course. Now we're going to say proxy box equals contract dot from ABI box v2 proxy dot address box v2 dot ABI, and we're going to grab both this and this from Brownie. And what we're going to try to do is slapping this ABI onto this proxy address, we're going to try to call a function only box v2 can call. However, we know that, like what we tested before, it actually should revert. So we can actually check for reverts by importing pytest, and we can say with pytest.raises, and I know that this is a Brownie exception. I know what type of exception this is. It's an exceptions.virtual machine error. You can figure out what type of error this is by just running it and getting the error. So this is actually from Brownie, this exceptions thing. So we're going to actually also import exceptions from Brownie. We're going to say proxybox.increment from account. And I saved and everything, sorry, got formatted here. But calling proxybox.increment should throw this exceptions.virtual machine error. So this test will pass if this throws an error. And that's how we test that. So we want this to throw an error the first time we call it. Then we're going to upgrade, and then we'll call it again, and it'll actually work. Now we're going to call upgrade on account, proxy, box v2, proxy admin, contract equals proxy admin. We're going to need to grab upgrade from our helpful scripts. And now we should actually be able to call increment with our proxy box. So first we'll do a quick assert, proxybox.retrieve equals 0. Then we'll do proxybox.increment from account. And then we'll assert proxybox.retrieve is 1. So we're deploying our box, we're deploying our proxy and everything around it. Then we're deploying our v2 implementation. We're trying to call increment, which won't work. We then upgrade our proxy to this new address, and then we can go ahead and call increment, and it should actually increment our box here. So let's go ahead and run this test. Brownie run test dash, Brownie test dash K. Grab this, paste it in. And we've done it. Our tests are working correctly, so we know that our box is working correctly. Awesome. Great job. Like I said, this is an incredibly powerful feature to be able to do these upgrades. With these, there comes a lot of risk, at least in the form of centralization risk. If you're the only wallet that controls the proxy, that means your application is centralized, full stop. So if you're going to deploy anything with proxies to mainnet, absolutely be sure to get it audited beforehand. Now, before we close this project up, let's actually deploy this to an actual testnet so that we can see everything that goes on when we call this deploy and upgrade. Let's go ahead and do it. So let's pop into our .env file and let's paste the variables that we have in here. We need the private key, Web3 Infura project ID, the Etherscan token. Awesome. Let's even publish the source of all these contracts so that we can see them on Etherscan. So for box, we're going to do a little comma here. We'll say publish source equals true. I'm just going to copy this comma to publish source equals true and paste it on all of my deployments. Publish source equals true. Publish source equals true on the admin, on the initial transparent upgradable proxy, on the box v2 deployment, and that's it. I've got my Etherscan token, my Web3 Infura, my private key. My brownie config is indeed pulling from the private key. My .env has .env. Let's check to see my wallet. We have some RinkB in here. Perfect. Let's do this. Brownie runs scripts, deploy and upgrade, network, RinkB. All right, so it looks like a couple of our contracts weren't able to actually verify. There are a couple bugs being worked out with some of the verifications, so we're going to ignore the ones that weren't able to be verified here. But let's go ahead, grab these addresses, pop them onto the RinkB Etherscan, and see what just happened. This is our box implementation. Let's grab this address. Let's paste it into the RinkB testnet Etherscan. Awesome. This is exactly what we have. Contract has been verified. This is exactly the code that we have here. And we can see all we have is a contract creation. And this is exactly correct. Because when we call the store function on this, it's actually going to get stored. We never actually called any functions directly on this contract. All we did was deploy it, which makes perfect sense. Let's go check out this proxy admin now. This second address, the second contract that we deployed. Sadly, this one didn't get verified. However, we can see we did indeed call this upgrade function at some point, which makes a lot of sense. If we look at our script, proxy admin, in our upgrade code, since we did have a proxy admin contract, we did call that upgrade function. Perfect, makes sense. Now let's go to this transparent upgradable proxy. This is going to be the most interesting one out of all of our applications. Interestingly enough, we look at this contract, we can see store and increment both have been called on this contract, not on the box. Because again, this is the proxy that we're going to call all the functions on to make our contracts upgradable. Internal transactions are calls that another smart contract made to this transaction. And if we look at a couple of these, we can see, if we click more, we had increment called from another contract, which makes sense. We had upgrade called from the proxy admin. And then we also, of course, we had store called from another contract. And if we verified this, we would be able to see Etherscan recognize this as a proxy contract as well. Hopefully when you work with this, you'll be able to verify it as well. But if not, not a big deal. You can always just manually do it later yourself. So this was an incredibly powerful project that we just did here and that we worked on. And all right, maybe take a nap, maybe go for a walk, get some food, get a drink, because we are on to our last coding project. Now, I do want to say that this project is considered a bonus because we're going to be going very quickly over the front end pieces. We're going to take all the building blocks that we've learned and build an amazing full stack application. Gear up, get ready, let's jump into this bonus project. And then after we finish this up, we're going to close everything out with a final quick section about security, the future, and thank you for joining this course. So let's do this last one. All right, now we are moving on to our final project. This is going to be the most advanced projects and combine all the knowledge that we've learned so far into one project. Then we're additionally going to put a front end or a user interface onto this project. When we build our own applications, we're going to need a way for non-devs to actually interact with it in a meaningful way. So now this isn't a front end or React tutorial course, although we will be explaining some of the choices that we've made and how to actually do them. You should be able to follow along fine, even if you don't have any front end experience here. If you're looking for a full front end tutorial, FreeCodeCamp has some amazing videos that you can absolutely try out. All right, welcome back, everybody. And now we're going to be embarking on the most exciting, the most end-to-end. We're going to take everything that we've learned and wrap it all together in this single last application here. And we're also going to be learning about front-end development. And we're going to be building a front end on top of our application, on top of our contracts here. Now, this isn't a front end tutorial. However, FreeCodeCamp has some wonderful, wonderful React tutorials. We're going to be teaching you guys just enough so that you can go ahead, jump in and build your own simple, but also kind of nice looking front ends on top of whatever contracts that you have. For those of you who want users to actually interact with your applications and interact with your contracts, building a usable front end is a really important piece. So let's take a quick walkthrough of what this application is going to look like. So here is our front end here. And what this application is going to allow users to do is it's going to allow users to stake or deposit their tokens into what's called our token farm contract. Once they have some token deposited, that's when you can kind of go get creative with what you want those tokens to do. You could use it as staking in some governance. You could go ahead and invest it in something like Aave or another DeFi protocol to gain interest. You could build a yield aggregator. There's a ton of different features that you can actually do once you have users stake their tokens. And here's how they would do it on their UI side. So we have this little button here, which we go ahead and click connect on. MetaMask is going to pop up and we're automatically going to sign in. That's going to connect our MetaMask to this user interface now. So if I look at my MetaMask, I'm on the Coven test network, and we can see that I am indeed connected. Now, what I can do is I can now stake some of my tokens into this contract. We currently have 3 different types of tokens that this platform allows for you to stake. Wrapped Ether, FIU, which is mimicking DAI on the test network, and our DApp token. This DApp token is going to be the reward token that our platform gives users as an incentive for staking on our platform. Once we stake, we can actually then unstake. And that's really it. So we'll go ahead and stake. Maybe we'll stake 10 DApp. We'll hit stake. MetaMask will pop up. This is the approve function, this first approve function that gets called. We get a really nice little waiting bar here. And once it's been approved, we get a notification saying the transfer has been approved. We then go ahead and we'll confirm staking. We'll get this little loading bar while it's being staked. And we'll see that pop up that says tokens staked successfully. Now, if we go to the token farm contract, we can see that we have 10 of this DApp token staked. We can also unstake it. The other thing that we can do is, as admins of this wallet, we can actually issue a reward to our users based on how much they've staked. So you see right now we have 95 DApp token. We have 10 DApp tokens staked. On the back end, I'm going to run an issue token script. It's going to send all users that have some stake a little bit of a DApp token reward. Now you can see it's been updated and we've been given a little bit of DApp token that resembles the amount of DApp token that we have staked. The way that we figure out the value of all of our different tokens is using, of course, Chainlink price feeds. We can then, of course, unstake everything. And we see tokens unstaked successfully. And that's it. And this is what we're going to build. Now, we aren't going to go over the unstaking portion of the front end application here, but here's what it would look like if you were to go ahead and finish building out the front end yourself. There is a full repository with the entire front end with this unstaking piece, but for simplicity, we're just going to skip over this unstaking bit. So let's go ahead and get started. I'm going to go ahead and make a new directory called DeFi stake yield brownie. And then I'm going to open this up in a new text editor. Now, the first thing, of course, that we want to work with is going to be our contract. So we're in here, remember, always start with brownie init, or you can start with the Chainlink mix. I'm just going to go ahead and start with brownie init. And perfect. Here is our setup. All right, first thing we're going to do is we're going to make our daptoken.sol. This is going to be the token that we're going to give out to users who are staking on our platform. This is our reward token. You might have heard of yield farming or liquidity mining. This is our token that allows users to actually engage and participate in that. And this is just a regular old ERC20. So you guys already know we've done this before. And for this one, we're even going to use the latest and greatest in Solidity. Remember, I said that you're going to have to get really good at bouncing around between Solidity versions. So for this one, we're going to do everything in 0.8. So let's go ahead and do that. So we're going to do pragma Solidity 0.8.0. And we're going to do this the exact same way we made our other ERC20 token. We're going to go ahead and use OpenZeppelin again. We can even just copy paste the import from their documentation, or we can just write out import at OpenZeppelin /contracts /token /ERC20 /ERC20.sol. And you guessed it, because we're using this at OpenZeppelin syntax, we're going to make a new file. Routing config.yaml. We're going to make some dependencies. We'll do OpenZeppelin /OpenZeppelin contracts. This time we're going to actually use version 4 of these at 4.2.0. And again, you can find out everything about this package by going to OpenZeppelin /OpenZeppelin contracts on GitHub. And then compiler, sulk, remappings at OpenZeppelin equals this part right here. Paste it in. Okay, great. Then what we can do, we can go back to our dApp token and just do some basic ERC20 bits here. So we'll do contract dApp token is ERC20, and we'll give it our constructor, public ERC20. We'll call it dApp token, and we'll give it a symbol of dApp. And we'll give it an initial supply as well. So we'll call the mint function, and we'll set the message.sender as the owner. Give it an initial supply of 1 million, which will be 1, 1, 2, 3, 1, 2, 3, plus those 18 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. And now that we have our first contract, we can try to compile it. Brownie, compile. And looks like it worked. Great. Now we're going to go on to create our more interesting contract, our token farm. We can even take a quick second and figure out what we want this to be able to do. Well, we want to be able to stake tokens, unstake tokens, issue tokens. This is going to be issuing those token rewards. We're probably going to want to add allowed tokens to add more tokens to be allowed to be staked on our contract. And we're probably going to want some type of getETH value function where we can actually get the value of the underlying staked tokens in the platform. With that in mind, let's move on. So, you know the drill, pragma solidity, caret 0.8.0. And we're going to be here for a while, so I'm going to close those out. And this will be our contract token farm, contract token farm. Oh, and let's not forget our SPDX license identifier of MIT. Well, let's go ahead and start with the staking of the tokens, right? Because that's going to be the most important piece of our application. So we're going to do function, stake tokens. They'll probably want to stake an amount of token, and they'll probably want to stake a certain address of the token. So some amount of some token. Now there's a couple things we need to keep in mind here. What tokens can they stake? How much can they stake? So these are our first two questions. For our application, we're just going to say you can stake any amount greater than 0. So we can even add that. We'll do require amount is greater than 0. And if it's not, we'll just say amount must be more than 0. And since we're using version 8, we don't have to worry about anything to do with safe math, which is awesome. So we can just go ahead and do stuff like this. Now we only want certain specific tokens to be staked on our platform. So we could say require token is allowed or something to this effect. So we might have to actually create a token is allowed function. So let's go ahead and create that function. Token is allowed. It'll take some token address, make it a public function, and it'll return a Boolean. It'll return true if that token's allowed, or false if it's not allowed. So how do we know if a token is actually allowed? We probably want some list or some mapping of these tokens and whether or not they're allowed. After all we've learned, you'll probably learn that there definitely are some trade-offs between lists and mappings here. For simplicity's sake, we're just going to stick with a list for now. So we're going to create an address array. We'll make it public, called allowed token. And this will just be a list of all the different allowed tokens. For our token is allowed function, we'll just loop through this list and see if that token is in there. So we'll do a for loop. For uint256 allowed tokens index equals 0. Allowed tokens index is less than allowed tokens dot length allowed tokens index plus plus. So we're going to loop through this list and we're just going to say if allowed tokens of allowed tokens index equals this token, then we're going to return true. Otherwise, if we get through this whole for loop and we don't find this token in here, we're just going to return false. Now we have a way to check to see if allowed tokens are there. Let's actually write a function to add allowed tokens. So we can do function add allowed tokens, address token, public function, and we'll do allowed tokens, and we'll just push it onto that array. Now adding allowed tokens is probably something we only want the admin wallet or the owner of this contract to do. So we'll add only owner as a modifier to this function, and we'll make this token farm ownable, is ownable, and we'll import from OpenZeppelin here too. Import at OpenZeppelin/contracts/access ownable.sol. Let's do a quick compile. Great, things are being compiled fantastically. Now that we have a little bit of functionality here, now might be a good time to actually go ahead and start writing some tests, if you want to. Since I know that we're going to change the constructor a little bit and we're going to change a little bit of how this is actually formatted, I'm just going to keep going. But now might be a great time, should I start writing some tests for my application? You know we're going to do those tests later on anyways, though. All right, great. But in any case, now that we have these two functions, we can go ahead and actually start checking to see if the tokens that these stakers are going to stake is actually allowed. So what we can do now is we can add this require statement in. We can require token is allowed of token. Otherwise, we'll just say token is currently not allowed. And perfect. Now we have two require statements that answer these questions. What tokens can they stake? And how much can they stake? So now all we have to do is we just have to call the transfer from function on the ERC20. Remember, ERC20s have these two transfer type functions. They have transfer, and they also have transfer from. Transfer only works if it's being called from the wallet who owns the tokens. If we don't own the token, we have to do transfer from, and they have to call approve first. So we're going to call the transfer from. Function on the ERC20 since our token farm contract isn't the one that owns the ERC20. We also have to have the ABI to actually call this transfer from function. So we're going to need the iERC20 interface. We could go ahead and pop it in here. We could also make an ERC20 contract. We could also just grab it from OpenZeppelin. So we'll do import at OpenZeppelin/contracts/token/ERC20/IERC20.sol. We're using the interface here because we don't need the whole contract. Anyways, let's now wrap IERC20. Let's wrap this token address as an ERC20 token. So now we have the ABI via this interface and the address, and we'll call that transfer from the message.sender, and we'll send it to this token farm contract. So from whoever calls stake tokens to this token farm contract, and we'll send the amount. And perfect. Now we just need to keep track of how much of these tokens they've actually sent us. So we're going to want to create some type of mapping here. And this mapping is going to map token address to staker address to the amount. This way we can keep track of how much of each token each staker has staked. So it's a mapping per token, per staker, per amount. So we'll just call this mapping of that token address, which is going to get mapped to another mapping of those user addresses, which then gets mapped to a uint256. So we're mapping the token address to the staker address to the amount. We'll make this a public mapping. And we'll call it staking balance. Now that we have this mapping in our stake token function, what we can do is we can say staking balance of this token from message.sender is now going to equal whatever balance that they had before plus the amount. All right, this is great. Now we have a way for users to stake different tokens that we've actually allowed them to stake on our platform. Awesome work. So what do we want them to be able to do next? We want them to unstake tokens. We want to be able to issue some reward. We want to be able to get the ETH value based on that reward. Typically, you might want to do this unstake tokens bit first. However, I know that we're actually going to need some additional functionality in our stake tokens function for us to actually issue tokens properly. So let's just go ahead and do this issue tokens bit. Remember, this issue tokens is a reward we're giving to the users who use our platform. So we want to issue some tokens based off the value of the underlying tokens that they've given us. So for example, maybe they've deposited 100 ETH, and we want to do a ratio of 1 to 1. For every 1 ETH, we give 1 DApp token. That's pretty easy for us to figure out. However, let's say they have 50 ETH and 50 DAI staked, and we want to give a reward of 1 DApp token per 1 DAI. Well, then we'd have to convert all of our ETH into DAI so that we know that conversion ratio for the DApp token. So that's the problem that we're going to work on now. Let's create this function called issue tokens. And this is going to be a function only callable, again, by the owner or the admin of this contract. So how do we actually go ahead and issue tokens here? Well, the first thought would be to loop through a list of all the stakers that we have. But right now, we don't have a list of stakers. What do we have? We have a mapping of stakers, and we have a list of allowed tokens. Well, we're probably going to need to have a list of stakers. So we'll do an address array, because again, we can't loop through a mapping. So we'll do an address array, we'll make it public, called stakers. This is just a list of all the different stakers on our platform. Now, when somebody stakes a token, we're going to have to update this list. We want to make sure they're only added if they're not already on the list. So in order for us to do this, we should get an idea of how many unique tokens a user actually has. So I'm going to create a function called update unique tokens staked with message.sender and the token. And what this function is going to do it's going to get a good idea of how many unique tokens a user has. And if a user has one unique token, we can add them to the list. If they have more than one, we know that they've already been added to the list, so we don't need to add them there. So let's create this function, update unique token staked. We'll have it input an address user and an address token. And we'll make this an internal function so that only this contract can call this function. And what we'll say is if staking balance, let's even do a little underscores here, of token of user is less than or equal to 0, we're going to update some unique tokens staked mapping. So we'll say unique tokens staked of the user is going to equal the unique token staker of the user plus 1. And since we have this new mapping called unique token staked, we'll make that as well. So we'll do a mapping of an address to a uint256 public called unique tokens staked. So this way we know how many different tokens each one of these addresses actually has staked. Now that we have a better idea of the unique tokens each one of these users has staked, what we can do is we can figure out whether or not we want to push them onto this stakers list. If they're already on there, we don't want to push them on there. If they're not on there, then we do want to push them on there. So what we can just do is say if unique token staked of message.sender is equal to 1 if they have one unique token staked. If this is their first unique token, we're going to add them to that stakers list. So we'll say stakers.push message.sender. And this is going to be our completed stake tokens function here. So we had to add this little extra functionality between the unique tokens to figure out how to actually issue some reward for them. But now that we have this list and it's going to get updated here, and it'll also get updated when we unstake, what we can do now is just loop through this list of stakers. So we can say for uint256 stakers index equals 0, stakers index is less than stakers dot length, stakers index plus plus, and now we're going to issue some of these tokens here. So we're going to say the address recipient equals stakers index. So one at a time, we're going to loop through, grab these recipients, and then we're going to send them a token reward based on their total value locked. So we got to do a couple things here. We have to send them a token reward. We have to figure out how to actually send them this token. And then we also have to get their total value locked. So let's do this. To send them a token reward, this is going to be this DApp token that we created in the beginning. This is going to be our DApp token. So right when we deploy this contract, we need to know what a reward token is actually going to be. So what we can do is right at the top, and then I'm actually just going to move this array up here so that they're all kind of nicely together. What we need to do is we need to create a constructor. Right when we deploy this contract, we need to know what is the address of the DApp token. What's the address of the reward token that we're going to give out? So we can say constructor. It will be passed an address of the DApp token address. This will be a public function. And we'll store this DApp token as a global variable. So we can say IERC20, since we're already importing it here, public DApp token. What we can do now is set DApp token equals IERC20 underscore DApp token address. So now we have this DApp token with its associated address. And what we can do now is call functions on it. For example, we can call DApp token transfer. We can call transfer here because our token farm contract is going to be the contract that actually holds all these DApp tokens. And we're going to send this token to the recipient, of course. But how much are we going to send? Right? How much of this token are we going to send to them? Well, we need some function to get the total value. So we're going to say uint256 user total value equals some function, right? And we can go ahead and define that right now. We'll call this function get user total value, right? Or get recipient total value, or whatever you want to say. So we'll pop recipient in here, and let's go ahead and create this function. So we'll call function get user total value address user. And this is where we do a lot of looping, right? We're gonna find out how much each of these tokens actually has. Now, what a lot of protocols do, instead of actually them sending and them issuing the tokens, is they actually just have some internal method that allows people to go and claim their tokens, right? You've probably seen that before, people claiming airdrops. That's because it's a lot more gas efficient to have users claim the airdrops instead of the application actually issuing the tokens, right? It's going to be very gas expensive to do looping through all these addresses and checking all these addresses, right? We're going to do it though, because we are a wonderful, amazing protocol and we want to give our users the best experience. But in any case, this is going to be a public view function that will return a uint256, right? Because we want to return this total value to our issue tokens function up here. So how do we actually get started here? Well, let's create a uint256 total value, and we'll set it off to, start it to be 0 here. And let's even start it off with a quick require statement, right? We want to require that the unique token staked of this user is going to be greater than 0, right? And if it's not, we'll say they don't have any tokens staked, right? So the value is going to be nothing. Now, if this is true, if they have some tokens staked, we'll go ahead and find it. So we're going to loop through those allowed tokens up here, the allowed tokens, and we're going to find how much this user has for each one of these allowed tokens. So we're going to say for uint256 allowed tokens index equals 0. Allowed tokens index is less than allowed tokens dot length allowed tokens index plus plus. And let's go ahead and we'll add the total value. And now we'll say the total value is going to be equal to the total value plus however much value this person has in these tokens, in this single token. So get user total value is the total value across all the different tokens. We need a way to get the total value across one token. So we're going to create a new function called get user single token value, and we'll pass it our user, and we'll also pass it this single token that we're on right now. So we'll pass it allowed tokens, allowed token index. So we got to create a new function here. Function get user single token value. This is going to take an address of a user and an address of a token. It's going to be a public function. I'm just going to put this on a new line to make it a little easier to see. It's going to be a view function, and it's going to return a uint256. We want to get the value of how much this person staked of this single token. So for example, if they've staked 1 ETH and the price of 1 ETH is $2,000, we want to make sure that this returns 2,000. Or if they have 200 DAI staked and the price of 200 DAI is $200, we want to make sure this returns 200, right? So we're getting that conversion rate. We're getting exactly how much value this person has staked in our application. Now we'll do a quick if. We'll say if unique token staked of the user is less than or equal to 0, then we'll just go ahead and return 0, right? We don't want to do a require here, right, as we did up here, because we want this to actually keep going, right? If this is 0, we don't want the transaction to actually revert, okay? We want this to keep going. So how do we actually get the value of a single token? Well, we're going to need to get the staking balance, right? But we also need the price of that token. So we're going to need to get the price of the token and then multiply that by the staking balance of the token of the user. So once again, we need to create another function. We'll call this one get token value. So in another function, we're going to call get token value. Get passed an address of a token. We'll make this a public view function that will return a uint256. And this, of course, is where we need some pricing information. And this is where we're going to actually work with the Chainlink price feeds once again. And hopefully this part is going to be a little bit more familiar for you. So what we're going to need is a price feed address. That's the first thing that we're going to need. So we're going to actually have to map each token to their associated price feed addresses. So we're going to need some mapping that does that, right? So we're going to need some mapping that's going to map an address to an address. It's going to be a public one, and this is going to be token price feed mapping, right? It's going to map the token to their associated price feeds. And with that, that means we're going to have a function called set price feed contract, where we actually set the price feed associated with a token. So this will take an address of a token and an address of a price feed. This will be a public, and this will be only owner. We don't want anybody to be able to set what this price feeds should be. We just want the owner to be able to do this. So we'll do token price feed mapping of the token is going to equal the price feed. And that's it. So now we have a way to set the price feed contracts. We have a way to map the tokens to their price feeds, right? And again, we go to docs.chain.link. We can go to price feeds, Ethereum price feeds. We can find these different price feeds here. And this is where we're going to set those price feeds. Now back down in our get token value, we can grab that price feed address now by saying address price feed address is going to equal that token price feed mapping of that token parameter. And now that we have this, we can use it on an aggregator v3 interface. Again, we can always go back to the docs here. We can grab this bit right here. Of course, we're going to change it to be 0.8. And for those of you who would rather I just wrote it out, we're going to import at chainlink/contracts/src/interfaces/aggregator v3 interface.sol. And since we're doing this import, we're going to go to our Brownie config, smart contract kit /chainlink Brownie contracts. And we're going to see what's the latest version of these. Now I'm going to point something out. This package recently changed to mirror the NPM package versions. So it does look like it went backwards in versions, and there's even a little update here. But this is the newest version, even though it says 0.2.1. It's literally just to match the NPM contract tags. So this is what we're going to use. So we're going to do at 0.2.1. And then in our remappings, we'll also do at chainlink equals this bit right here. Now that we've imported that, we can now grab that aggregator v3 interface or that price feed and say aggregator v3 interface of price feed address and grab that price feed contract. Then once we have this price feed contract, we can call .latest round data. And again, you can always check back to the documentation to see what that function actually looks like. And this is going to return, it's going to return a whole bunch of stuff. But we only care about the price. So the first thing it returns is round ID. We don't care about that, so we'll just put a comma. We do care about the int256 price, so we'll put that in there. But we don't care about the rest of these. So we'll just do comma, 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 because we only care about the price here. We also care about the decimals. We need to know how many decimals the price feed contract has. That way we can match everything up to be using the same units. So we'll say uint256 decimals